ISO 14644-14 is designed to address the important challenge of assessing whether equipment is suitable for use in cleanrooms by focusing on airborne particle concentration. It provides a standardized approach to ensure that materials, tools, and machinery do not introduce contamination risks into these sensitive environments. This helps maintain the integrity of cleanroom operations and ensures they meet strict cleanliness standards. The standard is a valuable resource for cleanroom users, quality assurance, and validation teams, helping them make well-informed decisions. It is especially useful when considering new equipment purchases, investments, or managing changes within the cleanroom. By following ISO 14644-14, stakeholders can achieve compliance and improve operational efficiency. A key focus of the standard is contamination control, specifically managing airborne particle concentration. It ensures that the equipment used does not compromise the controlled environment, which is crucial for industries where contamination can have serious consequences. This emphasis helps protect product quality and safety in critical cleanroom applications. The scope and purpose of ISO 14644-14 focus on linking cleanroom air cleanliness classification directly to the suitability of equipment used within these controlled environments. The standard evaluates the particle concentrations emitted by various equipment to ensure they are compatible with the specific cleanroom classification, helping maintain the required cleanliness levels. ISO 14644-14 has broad applicability across many types of equipment, including machinery, measuring devices, process equipment, components, and tools. This wide scope ensures that all equipment used in cleanroom operations is assessed for its impact on air cleanliness, supporting comprehensive contamination control. The standard specifically assesses particle sizes ranging from 0.1 micrometers to 5.0 micrometers, which aligns with the classification criteria defined in ISO 14644-1. By focusing on this particle size range, the standard effectively addresses the typical contamination concerns encountered in cleanroom environments. For the test environment, it is essential that it meets cleanroom standards by being at least one ISO class cleaner than the intended operational cleanroom. This higher standard ensures that testing conditions are more stringent, which helps maintain the integrity of the assessment results. Additionally, the environment must have strict particle source control, meaning no extra particle sources should be present that could skew the measurements. This eliminates external factors and keeps the focus solely on emissions from the equipment being tested. Unidirectional airflow is also required in the test environment. This airflow design isolates equipment emissions by preventing contamination from outside sources, ensuring that the particle concentrations measured are only from the equipment itself. By following these requirements, cleaner environment, controlled particle sources, and unidirectional airflow, we can ensure that the particle concentration measurements accurately reflect the equipment's emissions. This guarantees reliable and valid assessment results, providing a clear representation of equipment performance. The measurement methodology begins with a visual inspection of the equipment. This initial step helps identify any contamination risks and verifies that the equipment is intact and suitable for further evaluation. Next, we focus on measuring airborne particle emissions. Critical locations on the equipment are selected for these measurements, which are essential for understanding the levels of contamination present. After collecting the data, it is processed and analyzed to quantify particle concentrations. This detailed analysis provides a clear picture of contamination levels and is key to assessing the equipment's cleanliness. Finally, the results are linked to the ISO 14644-1 classification system. This connection determines the equipment's suitability for use in cleanroom environments and ensures compliance with international cleanroom standards. This slide covers optional additional tests in equipment assessment as outlined in ISO 14644-14. These supplementary tests are designed to enhance the evaluation process by providing a more comprehensive understanding of equipment performance. They go beyond simply determining basic suitability and offer deeper insights into how the equipment behaves. One key test is the total particle emission measurement. This test quantifies the overall contamination potential of the equipment, which is essential for assessing its impact on cleanliness in controlled environments. Another important test is operational life cycle testing. This evaluates emissions during extended use, helping to ensure that the equipment maintains reliability and consistent performance over time. Together, these tests help provide a thorough assessment of equipment suitability and performance in critical applications. In the preliminary agreement and planning phase, it is essential for the customer and supplier to work together to establish specific particle size ranges for evaluation. This collaboration ensures that both parties clearly understand the scope and focus of the assessment, aligning expectations and helping to achieve accurate results. Next, the reference air cleanliness classification must be determined according to the ISO 14644-1 standard. This standard serves as a benchmark for evaluating particle emissions in controlled environments, and adhering to it guarantees consistency and reliability throughout the assessment process. Additionally, it is important to identify the types of equipment and operational modes to be tested before the assessment begins. This step allows the evaluation to be tailored to the specific conditions of the equipment, ensuring that all relevant scenarios are considered during testing. Finally, each operational mode should be assessed separately. Conducting separate assessments for each mode captures all potential particle emission scenarios, providing a thorough evaluation and minimizing the risk of overlooking critical emission factors during testing. The representative mode of operation is essential for accurately capturing particle emission scenarios. By defining it clearly, we ensure that our assessment truly reflects how the equipment behaves during actual use. This approach allows us to understand the real impact of the equipment under typical operating conditions. When selecting operational parameters, it is important to choose those that mirror typical equipment use. Identifying the most representative conditions helps us achieve realistic and meaningful assessment results. This careful selection is key to the accuracy of our evaluation. We must include all relevant operational modes, especially when the equipment can operate in multiple configurations. For instance, we need to consider scenarios both with and without product present. This comprehensive inclusion guarantees that no critical mode is overlooked in our analysis. The testing space must be at least one ISO class cleaner than the intended target cleanroom class. Keeping particle levels low is crucial for obtaining accurate and reliable particle emission measurements. Airflow velocity should be carefully controlled, with a recommended vertical velocity between 0.3 and 0.5 meters per second. Proper airflow management helps us understand particle movement and prevents contamination during testing. Temperature control is also important, with the environment maintained between 18 and 25 degrees Celsius. Consistent temperature conditions help ensure stable testing and reduce variability in the results. Finally, humidity levels need to be kept between 30% and 70% relative humidity. Maintaining proper humidity prevents moisture from interfering with the tests, ensuring that measurements are reproducible and reliable. The visual inspection process begins with a pre-test examination, where all packaging materials are removed. This step is essential to prevent any contamination or interference during the testing phase and establishes a clean, controlled environment for the inspection. Next, inspectors conduct a thorough check for any physical damage or defects in the equipment. Ensuring the equipment is in optimal condition at this stage helps avoid potential failures during operation and guarantees accurate test results. The inspection also includes validating the correct assembly and configuration of the equipment. Proper assembly is critical to ensure the equipment functions as intended, and this step confirms that all components are correctly positioned. Verification of utility connections is another key part of the inspection. Inspectors check connections for power, water, and other necessary utilities to ensure the equipment is ready for operation. Finally, a qualitative evaluation of surface cleanliness is performed. This focuses on detecting particles, surface films, and proper lubricant placement. Maintaining cleanliness standards is vital for the integrity of particle emission results and overall test accuracy. The process begins with systematic scanning to locate zones that have the highest particle emissions. This scanning specifically targets critical areas such as moving parts, utilities, and interfaces, which are often the main sources of contamination. Sampling strategies involve varying the probe position and distance, which helps detect particle emission hotspots. Adjusting the probe placement is essential for accurate identification of these areas. During scanning, feedback can be either visual or acoustic, depending on the laser particle counter model used. These feedback mechanisms assist operators in real-time detection, improving the efficiency of the process. Pre-test findings, such as previously identified contamination sources, are incorporated into the scanning process. This enhances the accuracy of detection by providing valuable insights for targeted scanning. Finally, the qualitative scanning approach guides the transition to a precise measurement phase. This step is critical for conducting a detailed analysis of the identified hotspots and achieving an accurate contamination assessment. In this section, we focus on the precise determination of high particle count locations through detailed measurement protocols. We use laser particle counter with an air sampling volume of at least 28.3 liters per minute, and the probe opening is limited to 20 centimeters squared to ensure accuracy. The sampling probe is geometrically adjusted for optimal performance, with systematic positioning applied at identified high particle count zones. This careful adjustment ensures accurate data collection from the targeted areas. Sampling probes are systematically positioned at these high particle count zones, with each location carefully documented along with the exact probe positioning. This guarantees thorough coverage of all potential particle emission areas. At this stage, we collect localized, high-resolution data on particle sources. Detailed documentation supports the precision of the data, providing comprehensive insights into particle emission zones. Finally, exact probe positioning is crucial to ensure comprehensive coverage. By systematically addressing all potential particle emission areas, we maximize the reliability of the collected data. When selecting locations for suitability measurements, it is important to focus on locations with the highest particle concentrations identified during precise determination. This approach ensures that the most critical areas are evaluated for equipment cleanliness, which is essential for maintaining operational standards. At a minimum, one high particle concentration location must be measured to assess equipment cleanliness. This baseline measurement provides a fundamental understanding of particle emissions and serves as a starting point for further evaluations. Additionally, optional points of interest, such as product handling areas, can be included in the assessment. These additional measurements offer a more comprehensive evaluation of particle emissions and are relevant to operational use, enhancing the overall assessment. During the final measurement, sampling duration is set at 100 minutes, during which 100 individual samples are collected. This extensive sampling ensures statistical robustness and provides comprehensive data for analysis. It is important to maintain strict documentation of the measurement equipment's operational parameters, including the specific modes of operation, the number of operational cycles, and the positioning of the equipment during testing. This careful documentation helps maintain consistency and accuracy. Additionally, environmental conditions are recorded throughout the testing process. Monitoring these conditions is crucial to ensure the reliability and integrity of the results. Data processing transforms raw particle concentration measurements into statistically meaningful information. This step is essential to determine the equipment's cleanliness classification. It provides a reliable assessment of particle emissions. For high particle counts, procedure A is used when the expected counts exceed 10 per measurement. This procedure calculates the arithmetic mean to assess the reliability of the data. Additionally, upper confidence limits are determined to ensure accurate evaluations. This approach is specifically designed for situations with higher particle concentrations and emphasizes reliability in the statistical analysis. On the other hand, procedure B is applied when particle counts are 10 or fewer. It uses a conservative, probabilistic method that accounts for the increased uncertainty associated with low particle concentrations. The focus here is on a cautious assessment of emissions, ensuring careful and appropriate statistical analysis for low particle counts. In both procedures, at the final step, the test results, particle counts for specific particle sizes, are compared with the cleanroom class limits specified in ISO 14644-1. The test report includes information on the environmental conditions during testing, such as the air cleanliness class, the temperature, the relative humidity, and the average airflow velocity in test zone. It also describes operating conditions of the tested object, provides details about the measuring equipment used and specifies the locations of the critical measurement points, together with the measured number of particles in different size ranges at each location. The cleanroom suitability statement is a critical component of the test report. It specifies the cleanroom cleanliness class in which the tested equipment can be used. BNT Sigma is an independent testing laboratory that specializes in cleanroom materials. It conducts product assessments following the ISO 14644-14 standards, ensuring that materials meet strict cleanroom requirements. The laboratory features an ISO Class 2 particle emission laboratory, which allows it to perform highly accurate particle emission tests for environments ranging from ISO Class 3 to Class 9. In addition to testing, B-NT Sigma supports product development by providing comparative analysis and valuable insights. This helps manufacturers assess and improve their products to effectively meet cleanroom standards. Furthermore, the laboratory offers supplier evaluation services to ensure that suppliers comply with cleanroom standards. This is a critical part of maintaining overall quality in cleanroom environments. The testing process begins with an initial contact where you reach out to the laboratory via email to start the process. Be sure to provide detailed product information, including description, dimensions, weight, and return instructions to ensure everything proceeds smoothly. Next, you will receive a detailed quotation for the testing services. Take the time to review this quotation carefully to confirm it meets your needs. Once you are satisfied, accept the quotation to move forward. After accepting the quotation, you will need to ship the product to the laboratory in Poland. Make sure to follow any specific shipping instructions provided to avoid delays or issues. Test results will be available within 7 to 14 days after the product is delivered to the laboratory. Once the invoice for the testing is paid, you will receive the test report on the same day. In the following days, we will arrange the shipment of the product back to you.